This is about multiplication by numbers consisting entirely of nines and the astronomical applications of that. In Tirthaji's book he gives two quotes. The first one says, "Then comes a third corollary to the Nicolam Sutra, which relates to a very special type of multiplication and which is not frequently in requisition elsewhere, but is often required in mathematical astronomy, etc." And then later on in the same chapter, such multiplications involving multipliers of this special type come up in advanced astronomy, etc., and this sub-formula ekanyunena purvena is of immense utility therein. So here I want to show what Tirthaji might have been referring to here. So first of all, multiplying by numbers near to 100 but above it. Suppose you want to multiply 74 by 101. The answer is simply 74 repeated. The number gets repeated like that. And the same if you want to multiply 748 by 1001, you get the 748 repeated. So this is very simple, and the sutra is by one more than the one before because the number is just repeated like that. In the case of 74 times 1001, here we've got two figures, and here we've got a base that's got 3 zeros in it, so we have to think of that 74 as being 074, and that gets repeated. And then dropping the initial 0, we get 74,074. In the case of multiplying by 99, Tirthaji gives us a nice method, which is illustrated here. 74 by 99. We write down first of all one less than the number we're multiplying. So 74 becomes 73, and then we apply the sutra all from 9 and the last from 10 to the number we're multiplying by 99. So we take the 7 from 9 and the 4 from 10, and we get 26, and that gives us the answer 7326. And the sutra there is by one less than the one before in the reduction of the 74 to 73, and all from 9 and the last from 10 to get the second part of the answer. Another example, 748 times 999. Again, we reduce the first number, we get 747, and we apply the sutra all from 9 and the last from 10 to the 748 to get 252. That's the second part of the answer. And if the number of digits is not the same, we can imagine a couple of zeros before the 74 here, like that. And so we reduce the 74 by 1 to 73 and apply the all from 9 and the last from 10 to 0074 to get 9926. So multiplying numbers by a series of nines is very easy. Now, a little introduction to Pythagorean triples in case you're not familiar with this. A set of three numbers a, b, c we'll call a triple if the square of the first two added up equals the square of the third. So 3, 4, 5, for example, is a Pythagorean triple because 3 squared plus 4 squared equals 5 squared. Similarly here, minus 21, 20, 29 is a Pythagorean triple, and so is this one, 99, 20, 101. They're all triples. The last one there is illustrated here with a triangle because the first number is going to be the base of a right-angled triangle, the second is the height, and the third is the hypotenuse. And the angle is always the angle between the base and the hypotenuse. So we're going to have those rules for our Pythagorean triples. Now looking again at this triple 99, 20, 101, we may note the following. If we take the middle number there, the 20, we halve it and square. Okay, we halve 20 to get 10 and we square it, we get 100. And this number is one less than 100, and this number is one more than 100. Okay, the 99 is 100 minus 1, and the 101 is 100 plus 1. So there's a simple connection here between the outer numbers and the middle number. We can generate the outer numbers from the middle number, from that 20. We just divide it by 2, square it, and then do one less and one more. Extending this, we can develop further Pythagorean triples. Here's one. It's got a lot of big numbers, but it's a triple. And here's another one. What's nice about these triples is that the angles are very special. In this first triple, 99, 20, 101, the angle is 0.2 radians. In this one, it's 0.02 radians, and here 0.002 radians. So this makes these triples very easy to remember and to apply, and it's going to involve multiplying by a series of 9s. Now, in order to show how this works, we're going to have to look at triple addition, how you might add two triples up. So here on the first line we've got a triple ABC in which the angle is x, and a triple DEF in which the angle is y. And we're going to add them in such a way that we add the angles. So the triple that we get is going to have an angle x plus y, and this is how we get the triple, which has got that angle x plus y. We multiply vertically and subtract AD minus BE. Then we multiply crosswise and add BD plus AE, and then we multiply vertically CF. So it's obviously the vertically and crosswise sutra being used here. So let's see how this applies in actual practice. We've got a planet whose longitude is given by this triple. Okay, every triple defines an angle, and the angle there is L, the longitude. Doesn't matter what it is in degrees, it's defined by that triple. Find a triple for its new longitude when it has moved through an angle of 0.2 radians. So this is going to be triple addition, because we're going to take the given triple that gives us the position of the planet, and we're going to add the triple that's got an angle of 0.2 radians in it, which is this one here we've been discussing. So the angle is going to now be L plus 0.2. So we multiply vertically and subtract according to our formula here. We get this, 84 times 99 minus 13 times 20. You notice the multiplication there that we're interested in. Then, according to the formula, we multiply crosswise and add, so here and here. So 13 times 99 plus 84 times 20. So again, we've got this multiplication by 99. And then vertically on the right there. So we work these out because we know an easy way of doing this multiplication. We work it out and we get the answer. So let's just take another example. This time it's the same problem, but the triple now is different, the longitude is different, and we're adding a smaller angle on, 0.02 radians. And we know we've got a triple for 0.02 radians. There's the triple for L, and this triple for 0.02 radians is added. So again, we multiply vertically and subtract. We multiply crosswise and add, and then we multiply vertically. And again we get this multiplication by 9s coming up. So that makes the problem easy. We can extend this because there's another family of triples involving another number instead of 99. Suppose you want to multiply 74 by 199. If it was 74 by 99, we would reduce the 74 by 1. But because it's 199, we have to double first. We double the 74, then subtract 1 for the first part of the answer, and then we apply the sutra all from 9 and the last from 10 to 74 to get the second part, 26 again. So this comes to 148, 147, and then the 26. If we want to multiply by 299, then you probably guessed it, we have to multiply this number by 3 and subtract 1. And then put the 26 after it. And so we get 22126. So this is a nice way of multiplying by numbers of this type, 199, 299, and so on. And in fact there is another family of triples, which this is the first member, 399, 40, 41. And this is the next one, and you can see the pattern. And in fact the angles in these are 0.1 radians, 0.01 radians, 0.001 radians. So we can use these triples too, which is going to involve multiplications by 399 or this number and so on. So let's take an actual example to see how it works. A planet has a longitude given by this triple, and we want to find a triple for its new longitude when it has moved through an angle of 0.1 radians. Well, we know a triple for that. So this is the addition, this is the given triple for the longitude, this is the triple for 0.1 radians, and so we multiply vertically and subtract, like that. So here we're involved with that kind of multiplication we had before, 45 times 399, and then we multiply crosswise and add. Again we've got to multiply by 399, which we now know is easy, and then the 53 times 401. So we get the answer. Now going into 3 dimensions, triples are in 2 dimensions and quadruples are in 3 dimensions. So we have 4 numbers, x, y, z, r, such that x squared plus y squared plus z squared equals r squared. So 6327, for example, is a quadruple because 6 squared plus 3 squared plus 2 squared equals 7 squared. And the diagram here shows this. We've got 3 dimensions here, the x-axis, the y-axis, the z-axis. The origin is here. And there's our quadruple. We go 6 along the x-axis, 3 in the y direction, and then 2 in the z direction. We end up with at a point P here, which is 7 units from the origin. That's the 4th element. And the quadruple defines 2 planes, one in the xy plane, which for our astronomical purposes we're going to have the celestial equator, and we've got a plane inclined to that, ORP, which is going to be the plane of some planet moving in an orbit not in the equatorial plane. And the angle of the inclination of that orbit to the reference plane is I, the inclination, and the angle of the planet in its orbit is given by A. So here's an actual problem in 3 dimensions that we could look at. The equatorial rectangular coordinates of a planet at a certain instant are given by this quadruple, 12, 4, 3, 13. So in astronomy we often use these equatorial rectangular coordinates, which means we're using quadruples. Find its equatorial coordinates when it has moved in its orbit through 0.2 radians. So we're going to use this triple for 0.2 radians that we had earlier. And the quadruple equivalent to that is going to be this, which is the same except that we've converted the 20 into 1612. This is explained more fully in the paper itself, but basically the ratio here has to be the same as the ratio here, 4 to 3, and these 3 have to form a triple. It's very easy to work out the 1612 from the 20. Anyway, we then do our quadruple addition. So there's our given quadruple like we had in the case of the triples. There's the angle we want to add on, or the quadruple we want to add on, and we perform quadruple addition, which is not explained here, but it's in my book, Triples, and it follows a similar way to adding triples. So we multiply vertically in the first 3 columns and we add and subtract. So we've got 12 times 99 minus 4 times 16 minus 3 times 12. That's the first element of the triple for L plus 0.2. For the second element, we cross multiply in these two columns and add 4 times 99 and 12 times 16. For the third element, we cross multiply in the first and third columns. So we have 3 times 99 and 12 times 12. We add those up. And then we multiply vertically on the right there. And again we see this coming up, this multiplication by a series of 9s. And so we work that out to get the answer, which is the position of the planet required. So just to sum up, Tirthaji shows how to multiply by numbers consisting entirely of 9s. And he says that this very special type of multiplication is often required in mathematical astronomy. So this paper introduces two families of triples with memorable angles. First of all, we had this set, and then this one. And such small angles do arise in astronomical problems. These angles are very small. And using these in triple addition and quadruple addition, and also subtraction, involves multiplications detailed by Tirthaji.